Hi students, this is Madhu Dharmapuri. Welcome back to the electrostatics lecture series in which we are going to discuss about electric field due to a plane sheet of charge, infinite in size, non-conducting plane sheet of charge as well as conducting plate sheet of charge, one after the other. What is the electric field nearby a plane sheet of charge, infinite in size? Okay, so first we will calculate electric field due to an infinite plane sheet of charge which is non-conducting. Means just like you can imagine a paper of very thin size, or you can imagine this of any shape, any arbitrary shape, need not be a square or rectangle, it can be any shape. Okay, non-conducting means made of some plastic or made of some material which is not conducting electricity. Okay, so that is our first problem. So given a plain thin sheet of infinite in size, given a plain thin sheet of infinite in size with constant surface charge density sigma, means on that plane sheet which is non-conducting, the charge is distributed uniformly with surface charge density sigma, means in every unit area the charge is same with surface charge density sigma. Charge per unit area is given, that is sigma. See, if this is my sheet, in every unit area the charge is given. Surface charge density means that only. You can imagine, you can see this picture. The charge is like this. If of any arbitrary shape, I have taken one thin sheet of infinite in size, very big. See, infinite in size is nothing but the point where you are finding electric field nearby it is very near to the sheet, and size of the sheet is very big. See, when you are comparing the distance between the point where you are finding electric field and the sheet and the size of the sheet, if size of the sheet is very big in comparison with the distance of the point where you are finding electric field, then we can consider that sheet as infinite in size. It need not be of length infinity. Something which is very big when it is compared to the distance of that point from the sheet. Remember this. Okay, so this is the sheet on which the charge is distributed uniformly and charge per unit area is given, that is sigma, the surface charge density. And our aim here is to find out electric field at this particular point P, which is nearby this, at a distance of small r. Means something like this. See, if this is a sheet, I would like to find out electric field somewhere here, very near to it. Okay, so this is what the problem is. This is a side view actually. See, if I see from this side, if my sheet is this, if I see from this side, that is the side view. That is the side view. But front view will look like this. You can see. The front view will look like this. The charge is distributed. You don't see this side. You don't see the side of this. You will see only the charge on this. That is front view. Okay. So by symmetry, by symmetry, since the sheet is infinite in size, field must have the same magnitude and opposite in directions at 2 points equidistant from the sheet on opposite sides. For example, if this is a point P at a distance of smaller, if the electric field at that particular point is E at this point, what would be its direction? Away from positive charge, right? On the other side, at the same distance from this sheet, if this is a P, here also electric field will be same in magnitude but opposite in direction. That is what it is written. By symmetry, since the sheet is infinite in size, the field must have the same magnitude and opposite in direction, same magnitude, at 2 points, equidistant from the sheet, r distance from sheet, on opposite sides of the sheet. It's very simple. There's nothing to explain there. See, I have a sheet like this. On this side and on this side, at both points, if both points are equidistant from this sheet, and at those 2 points, electric field magnitude will remain same, but opposite in direction. This side it will be this way, and on this side it will be this way. That is what is written. Okay. Now, how to find out electric field at this particular point or at this particular point? Same magnitude. For this, I am going to draw a Gaussian surface, because we are using Gausslaw here. I am going to draw a Gaussian surface which must pass through the point my Gaussian surface is in cylindrical shape of any arbitrary length L. So this is a Gaussian surface. Here also I can draw the same front view. L length, R here, overall length is 2R. Here also overall length is 2R. And this length is L. See, both are same pictures. This is side view, this is front view. Both are same pictures. Okay, don't confuse with that. Gaussian surface is drawn in cylindrical shape. Okay, which has 3 surfaces, 2 flat surfaces, one, and this I am taking it as a curved surface as 2, and this flat surface as 3. 1, 2, 3. Okay, and if I consider one small area on this flat surface, that will be dA. Let us take it as dA, and on this side also it will be same, that is dA. Okay, so on this curved surface, let me take it as ds, because curved surface area is different from flat surface area. Okay, so here electric field is this way, so 90 degrees here. So the total electric flux passing through Gaussian surface will be total electric flux passing through Gaussian surface pi E equal to pi 1 plus pi 2 plus pi 3, which is nothing but integral E dot dA pi 1 means this one, plus integral E dot ds is second one, curved surface, plus integral E dot dA is third one, this flat surface. And if you observe from this picture, the angle between E and dA is 0 here, the angle between E and dA is 0 here, and hence it is EdA cos 0 plus EdS cos 90. You can check it here. Electric field is this way and ds is this way on curved surface, and this one EdA cos 0 on this side also. dA is this side, E is this side. So area vector dA, ds is also area vector. So what do we get? This is EdA plus EdS cos 90 is 0, so you can write it as 0, plus what is here? EdA, which means I can write it as E integral dA plus E integral dA, because E is same and constant. E is same and constant, you can see on 1 and 3. And one area is same, 3 area is same. Integral dA is what? Integral dA 1 is what? This flat surface area. Integral 3 dA is what? This flat surface area. Which means both are same. See, cylindrical, uniform radius, this side, both areas will remain same. So let us take that area as A, so that it will be EA plus EA, which is equal to 2EA. So integral dA, I am taking it as A. Means this area is A and this area is A. Circular area. 2EA. So this is the total flux passing through this Gaussian surface. By definition of flux, we have calculated this. So let us give this equation number 1. Right? Now we will see electric flux passing through Gaussian surface from Gauss law. Okay? So is this done? Okay. So I am removing from here. Let it be here. So pi E will be what? 1 by epsilon naught times charge enclosed by Gaussian surface. From Gausslaw, that is only. Total electric flux passing through Gaussian surface from Gauss law. is this one. So pi E is equal to 1 by epsilon naught. What is the charge enclosed by Gaussian surface? What is Gaussian surface here? This one. See, it is like this. If you can imagine, this is a plane sheet, and if this is my Gaussian surface in cylindrical shape, for example, imagine like that, and that is passing through this sheet, so it will be like this, passing through this one. I cannot pierce it into it, but you can imagine like this. It is in the middle of it, so I am just pressing it so that it is coming outside this side, so it will be like this. So this side also cylindrical in shape, imagine like that. Okay, so what is the charge enclosed by this Gaussian surface now? Only this area, only this area, only this area. How much is the charge inside it? This is charge enclosed by the Gaussian surface. See, the charge enclosed by this is Gaussian surface, this entire cylindrical. Is there any charge here? Is there any charge here? Is there any charge here? No, right? Is there any charge here? Any charge here? Any charge? No, right? Where is the charge in the Gaussian surface? The charge in the Gaussian surface is only in the middle part of it. Here. How much is it? Because it is going inside this. Okay, so that is how you have to imagine. The charge enclosed by the Gaussian surface will be how much? Sigma multiplied by A. Sigma is given. So sigma multiplied by A. This is the charge enclosed by the Gaussian surface. See how it is written? In 1 unit area, sigma is the charge. If area is 1, sigma is equal to charge. Then in A area, sigma A. In 1 unit area, sigma is the charge. If area is 1, sigma is equal to charge. Then in A area, what is this area? This area is A, right? See, this is A, this is A. So this should be A. What is this area? A, right? It's a cylindrical shape. So this side A, middle one also A, right? So that is how this is area A. So in A area, how much is the charge? Sigma A. That is how it is written. Okay. So this is equation number 2. And from 1 and 2, 2EA is equal to sigma A by epsilon naught. And AA gets cancels. E will be sigma by 2 epsilon naught. So this is our answer. This is our answer. So this is electric field due to an infinite plane sheet. This is electric field due to an infinite plane sheet of charge non-conducting. Remember, this is non-conducting. This one, sigma by 2 epsilon naught. So what is the electric field now here? Sigma by 2 epsilon naught. What is electric field now here? Sigma by 2 epsilon naught. And one more important point here. Here E is independent of R, distance of the point. What is R? Independent of small r. See this small r. From the sheet, what is the distance of the point? Smaller. It is independent of it. Remember this one, it's very important. E is independent of R. equal to sigma by 2 epsilon naught here and sigma by 2 epsilon naught here. Infinite plane sheet non-conducting. Okay, so now we will see electric field due to infinite plane sheet conducting. Plane sheet of charge conducting. How it will be different. Okay, now we will see that. Is this okay? Copy it. Right? Okay. Electric field due to an infinite plane sheet of charge conducting plate this time. Metal plate you can say. Okay. But this time the plane sheet is of thick in size you can say. Thickness. It has some thickness. It's not thin. You can imagine like let me show you some. This one for example. Of metal. Made of metal you can say. Okay, so charge is given to a conducting plate so that it distributes itself over the entire outer surface of the plate. The charge is distributed on this side and this side. Both sides. Charge is distributed on both sides because it is a conducting plate. Okay, the surface charge density sigma is uniform and is same on both surfaces. On this surface and this surface. This side and this side. Uniform charge is distributed with surface charge density sigma. Means in every unit area the charge is same. In every unit area charge is same. Okay, so this is how you can imagine. This is similar to the previous one, but the only difference is that this time the charges are on both sides. In the previous case, charge is on only one side, but in this case, the charge is on both sides. This side charge is there and this side charge is there because of its thickness and conducting, because it is a conducting plate. The charge given to it is accumulated on this surface as well as accumulated on this surface, uniform distribution. Everywhere in unit area, charge is sigma. This is the problem given to us. This is the side view of this problem. This is the front view. See, if I see from here, I will see like this. You can see plus, 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 plus. This is the thickness of this sheet. This is the thickness of this sheet. And from this side, you can see it is like this side view. So this is shown here, and the charge on this is shown here, and on the charge on back side is this one. I cannot show you that, but it is this one. Front view is this one. Front view is this one. Okay. So now what is our step now? We have to find out electric field at this point P or at this point P at a distance of r from it. So we should construct a Gaussian cylinder. So let me construct a Gaussian cylinder here. Similar to the previous one, only difference is the charge this time is on both sides. You can draw here also. Okay, so here you. What is the electric field direction? This side is E. This side it is E. If you consider this one, it is E here. It is E here. Because positive charge and electric field direction is always away from it. Okay, so now we will write electric flux passing through this Gaussian surface. Electric flux passing through this Gaussian surface, and calculate electric flux using Gausslaw and compare both of them. So copy it. Okay. So Gaussian surface is drawn. In cylindrical shape. And the total electric flux passing through Gaussian surface is pi e equal to, similar to the previous one, pi 1 plus pi 2 plus pi 3. Where is 1, 2, 3? You can see this is my 1, this is my 2, this is my 3. Here it is 1, 2, 3. Both are same. Okay? 1, 2, 3. And this, it is dA. Here it is dA. Here it is ds. And here it is 90 degrees. Okay? So pi e is how much? How much? Pi 1. What is pi 1? Integral e dA 1 plus integral e ds 2 plus integral e dA 3. Similar to that, you can say E dot dA it is actually. Okay, so what is E dot dA on first surface, first flat surface? E dA cos 0, right? So it is nothing but E dA cos 0 1 plus E ds cos 90 plus E dA cos 0. So I am writing direct steps. E integral 1 dA, because cos 0 is 1, plus 0 plus E integral dA, because E is constant and same. Similar to the previous steps. Okay. So pi E is equal to EA plus EA is equal to 2EA. Give it as equation number 1. So integral dA1 is area of this, circular area of this. Integral dA2 is, this is 3, is area of this. Okay. Here you don't need anything because E and ds are perpendicular, so it is 0. This we have calculated already in the previous one also. Okay. Now we will use Gauss law. Here you will get something different. The charge enclosed by the Gaussian cylinder is going to be something different in comparison to the previous one. Why something different? The charge this time is on both surfaces. In the previous case, charge is on only one surface. Okay, so that is different. Okay, is it okay? Done? Okay. So from Gauss law, total electric flux passing through Gaussian surface is how much? 1 by epsilon naught times charge enclosed by Gaussian surface. So here you have to be careful. What is the charge enclosed by the Gaussian surface? See, the Gaussian surface this time is like this. So here it is going through this actually. I cannot show you that. Okay, so Gaussian surface is this way. What is the charge enclosed by this Gaussian surface? Here it is not there, here nothing. But only when it is crossing this, when it is passing through this cross-sectional area and this cross-sectional area, both will have the charge. You can see this here and here. Here I cannot show you that. On this side I can show, but on the back side I cannot show. You can see, for example, let's see this one. This is back side and this is front side. If I press it like that and it is going out of it, so it will be like this. So two circular cross-sectional areas of this cylinder have charge, this and this. In the previous case, there is only one, because the charge is only on the one surface. But here we have charge on two surfaces. So charge on this surface is sigma A. See, charge on one surface is how much? 1 unit area, sigma is a charge. Right? In A area, sigma A. What is this area? A. What is this area? A. Right? So this area is A, right? So this area is A. This area is A. What is this area A? This area A. So in A area, sigma A is the charge. In A area, sigma A is the charge. So this time 1 by epsilon naught sigma A plus sigma A is the total charge enclosed by the Gaussian surface. So this is my Gaussian surface. Here the sigma A is the charge, here sigma A is the charge. You can see this. Sigma A is charge. Or here. So sigma A plus sigma A. Okay. So 1 by epsilon naught 2 sigma A. This is equation number 2 now. Right. So one we have this 2 EA, pi equal to EA. And from 1 and 2, two EA equal to 1 by epsilon naught 2 sigma A. A cancels, 2 cancels, and we are getting E as sigma by epsilon naught. Again, E is independent of R. This is the charge due to an infinite plane sheet conducting. This is electric field due to conducting infinite plane sheet. Conducting infinite plane sheet. See, in the previous case it was sigma by 2 epsilon naught. This case sigma by epsilon naught. So it is 2 times that previous electric field. See, in the previous case where it is of non-conducting, the charge is only once on one side, and electric field due to that plane sheet is sigma by 2 epsilon naught. Now if it is a conducting sheet, metal sheet, the charge is on both surfaces, the electric field is now sigma by epsilon naught, because due to one surface sigma by 2 epsilon naught, due to another surface sigma by 2 epsilon naught. So if you add both of them, see, electric field is equal to sigma by 2 epsilon naught due to charge on one surface. If you have charge on two surfaces, it should be 2 into sigma by 2 epsilon naught. That is what is sigma by epsilon naught. Okay. This is how you can calculate. If you know the previous one, you can just simply multiply by 2, because this time you have charge on both sides. If charge is only on one side, the electric field is sigma by 2 epsilon naught. If the charge is on both sides, electric field should be 2 into sigma by 2 epsilon naught. So it's sigma by epsilon naught. So electric field due to only one surface, the charge on one surface, sigma by 2 epsilon naught. If you have charge on both surfaces, sigma by 2 epsilon naught plus sigma by 2 epsilon naught, you will get sigma by epsilon naught. So this, in this way also you can understand this. Okay, so hope you have understood. If you have any doubts regarding this lecture, you can put your doubts under the comment section. Thank you very much.